So some of this deep learning intro slide has a bit of review stuff, so that might be useful or not. So trying to build up to this idea of what a neural network is going to be for, and it's learning a pattern, just like anything that we've been learning, right? We're learning the parameters of a function that is going to fit some data and help us predict a value, interpolate a value in between points we've never seen, give us the correct class label for some input features, but essentially give us a number output that is basically correct based on the inputs, and it knows that because it's seen it before, right? And so regression is a simple example of this, right? So in linear regression models, we talked about white ray at the beginning, you're learning a line where you're fitting a bunch of these weights so that you fit a line to minimize the error of that line going through the data points, right? It's kind of the simplest machine learning you could do. You're just fitting some parameters to fit that line, right? And then we talked about logistic regression, which is essentially using the same concept for optimizing a bunch of weights on a line, but the weights are on a line that is defined in this sigmoid function, this distribution that gives us logistic distribution. It gives us a number between 0 and 1. And so no matter what number we give into it, if it's positive infinity or negative 5 million or 2, it's going to give us a number between 0 and 1, so we can kind of treat it like a probability, and we can use that as the output for determining a classifier, right? And so we used that for classification. Well, so I'm still going to show. So we can see this logistic regression as a graphical model, and I think I showed this before when we were talking about it originally, that we've got a bunch of inputs, and these inputs are for every data point we're getting, the inputs are actually, you know, the different features that we're obtaining for every single data point. And we've got weights on all of those features that we can use to combine and get some function. And then we apply it through the sigmoid function, and we get this output, which can be treated like a probability, right? So that's the kind of thing. It's just another way to represent what we're talking about here, but you can start to see the structure of why they called it a neuron, right? Because you've got a bunch of inputs like in your synapse, and they're going into one thing, and somehow it's doing some magic in here that combines two distinct activities. One of them is combining the data in some way with weights that you can fit, and then applying a nonlinearity, right? So there's two kind of important steps here, and then you get this output, which you can treat as a probability or a spike or some kind of pulse, right? So, okay, I think we talked about this as a classifier. I'll just show this part as a picture. If you use that with a simple function, once you've got your threshold, once you've got your weights trained, you can use that as a classifier, because if it's above a certain threshold, say 0.5, then you say it's in one class. If it's below, it's in another class, right? So that was that's the main idea of logistic regression. I don't know if we talked about this before, though. Yeah, so a bunch of it is some review, but I'll show this part anyways. I just want to jump ahead to this part to show why we're talking about it. The main idea for neural networks originally was essentially to take that idea of a logistic regression process as a unit, right? So treating this as a repeatable unit, which is what we'll call a neuron, right, like in the brain, although much simpler than what's in the brain, because the brain neurons can take millions of inputs, or thousands at least of inputs, and they can have many outputs, and their outputs are continuous and complex. So it really is nothing like a neuron in a brain, but it looks like it physically. And so the basic idea of a neural network was this, that you essentially have, you draw up a bunch of variables and connect them using these, right? And so every single one of these nodes has a bunch of inputs, and they are basically this model. So every single node here on the inside and on the last layer are one of these, and they all have their own weights, right? And the weights are being trained, and that means it can learn, many different patterns, not just a single pattern, and learn something complex. That's the main idea. That's neural networks. Easy. This idea is people had in the 70s, and definitely in the 80s, people were talking about it and trying it, and it wasn't working particularly well, or was working well for very small problems. So the history of neural networks is how to make it work better. An important part of that, though, is that one way to train the logistic regression on its own is by gradient descent, and we're still using this today for neural networks. So if you just had a single neuron, you can represent it out as a function like this. You apply log like we normally want to make things a bit easier. So we like having the negative log likelihood, where we take that function, we apply negative log to it, and then getting the gradient of that is much easier. And so when we've got the gradient of this with respect to the weights, right, because it's got a bunch of weights that are being fit and altered. And so what we want to say is, what's the gradient with respect to the weights, right? And so what does a gradient mean? Right, the gradient means for every small change you make in the weight, does the value output of the function go up or down, right? That's all it ever means, right? And so if you wiggle, weight, 212, then does the output of the entire function go up or down? And if you wiggle it by the smallest possible amount, an infinitesimal change, does the value go up or down? So the gradient tells us that for every weight, does the function go up or down if you change that weight, right? And that can be computed analytically because we know the function. And then once we know the gradient, right, so g is the entire gradient of this, and then we have some step size, which says, because what you want to do is you want to, presumably, you want the values of this function to go up, right? And so if you weight it so that you say, one way to train logistic regression, right, is to say, find it on the positive example. So whenever it has an example where it got it right, basically scale it by the changes in the gradient that would make that happen and make those more likely, right? So you want to find the cases where your model got it right, so it got the right class, and you want to move the weights up to encourage whatever happened in that situation, right? And if it got it wrong, you want to push the weights down to discourage whatever happened in that situation. And that's what all of the training comes down to intuitively, right? And so we've got some set of the parameters theta, and why did I switch to theta on this? We're talking about W the entire time, and now it's theta. People often use theta for weights, so for some reason on this slide I have both notations. Maybe there's a reason that I've forgotten. But let's assume these are weights. They are WK and WK plus 1 to match these. Does that make sense? I think it makes sense. And then you update it, right? So you say that the new one is going to be, this is why it's the negative log, so we're going to subtract the gradient of the points based on that. And we have some learning rate, right? So learning rate is going to tell us how important every update should be, because you want to scale this to be some smaller number. Just a moment. Apologies, I had to go turn off the local fire alarm in our apartment. It's too high for my wife to reach it. Hopefully it's not a real fire. If there's a real fire, then this lecture will end abruptly, but I'll let you know. Our building's fire alarm goes off pretty frequently, so my prior belief that there is a fire is low. Okay, so that's an idea of gradient update. There's lots of linear classifiers that we've now learned and talked about. We have k-nearest neighbors. We're learning kind of a way to combine your scores from all your neighbors. We had naive Bayes, where we're combining independent probability models of input kind of features and saying they're just completely independent, but we're going to optimize that. And we have support vector machines, where we're learning a discriminant function that learns a linear function, but it's a divider function explicitly between data points. And so they're all kind of linear, right? I've got some repeated slides here, so we kind of ignore that. Another summary of support vector machines, which we've just finished talking about, so I don't feel like we have to talk about that again. Some of these slides, I think this deep learning lecture I use sometimes for intro for people like who aren't taking a course, so I'm summarizing a bunch of stuff in case someone had seen it, but we've gone through these recently. So, but remember, just again, in all of these cases, we're optimizing a linear function and coming up with some output. So in a way, they all have these similar patterns. How long does kernel machines go on? All right, this is the last one. Yeah, and I was mentioning this when we were talking about SVMs or kernel methods in general, because you could talk about SVM essentially as one type of kernel machine. So you could do lots of different things applying kernels and not just fitting a linear weight. You can imagine anything that basically has a kernel function in the middle that you use to split. But they all have that problem that you have to pick the kernel and very customized, so they don't generalize well beyond what you designed it for. So luckily, what people have realized kind of more recently is that all of these things actually can be seen as special cases of a neural network where it's learning the kernels automatically. So there's other names for these. You'll see sometimes multi-layer perceptrons, especially in like engineering literature, they'll call it this more often. So if you see MLP, they just mean simple neural network, which we'll talk about. A lot of people in engineering insist on calling them artificial neural networks to emphasize that they're not real neural networks like in a brain, which I think people realize. In computer science, people would just call them neural networks. And of course now I have to update my slide because now some people just say deep learning and they mean neural networks as well, even though by default the original neural networks were not deep, they were shallow. So you could say that there's shallow learning and neural networks and deep learning. But in a sense, they're all related, right? Because deep just means it's got more layers. So shallow and multi-layer perceptrons are all special cases of deep learning if you just adjust the number of hidden units. And really, yeah, that's the part that it's shallow. Shallow kind of means that these hidden layers are like, I don't know, 1, 2, maybe 3. That's shallow. And then deep is more than that, right? This is not a hard and fast rule, because if you just have a few layers, they may not say it's particularly deep, and there are models that are hundreds of layers deep, but it's very hard to do that. But even once you have 3 hidden layers connected together, you start getting into troubles mathematically, and that's what people had to figure out. But we'll go through the basics first so that we know all these terminology for how they all fit together. And today's things is really just the introduction, so if you know already basic neural networks and history, you probably won't get anything new out of this, but our next new lecture next Monday, we'll be going much deeper into all the modern things that help them work. So it's up to you. But if you don't really know how neural networks work, this is the basics. So we have these three layers. We have an input layer, a hidden layer, and an output layer. As I said, the hidden layer takes in multiple features and dimensions. Every input is a different dimension for a single data point and passes it to the hidden layer, right? And so the hidden layer are these sigmoid units, like we said. So they've got the every one of these has the sum and the sigmoid function built into them, right? And they're applying that, although we'll change some of those, what these functions are, how they're combined and how they're made nonlinear can change and be interchangeable, but the basic structure is the same. All that's essential is that this is a nonlinear function, and that is actually important that it's nonlinear. And then on the output you have something different, so at some point here you usually have another nonlinear function, but then you also have some kind of max or threshold, right? Greater than equal to something that gives you an actual value, right? And this can be a class, it could be a number, it could be a pixel, some kind of output that you can use to answer your problem. But they're all numbers at base. It's just you're turning them into something else if it's more than a number. Anything else, it has to be here. So the output could be nonlinear or not, but this part has to be nonlinear. Okay, so essential properties. And there's another slide that talks about this in more detail. For some reason I have them in two places. Okay, but that's getting into more details, I guess. Yeah, so there'll be another slide where we mention this as well, but it's an important part to think of that even the simple neural network, the multi-layer perceptron that we have there with a single layer of hidden units like this can represent any function that you can define, like that's actually a function in the mathematical sense, that it's defined as a function, so every input has one output, it's one, two, and on to, and all those things. Anything, so we can handle it. That's a powerful statement, and that's why people got excited about neural networks in the 70s and 80s when the idea first started. Like, oh, well, you could do anything with this because you've got enough parameters here that you can basically come up with all these different patterns and you can overlap them. So it's just like Fourier transform. You can represent any signal with a combination of sine waves weighted properly, right? So this is essentially the same thing, that as long as you define these functions and find the right weights for it, you can represent any input-output combination, every function. The question is, how many nodes do you need here, and how do you fit those weights? So mathematically, you can prove that any function is representable, but how many nodes you need? And I think on the later slide I have, it's like a lot, right? So you need something like 2 to the n hidden nodes to represent any function to be generally true. So that's a lot. It's not feasible to optimize those. And it's actually harder to optimize a single layer than to optimize multiple layers chained together, which people didn't realize at the beginning. But regularization is another issue. It's very easy for them to overfit, right? So we've talked about overfitting, right? So if you learn the exact outputs that only match the inputs, you're basically able to parrot back exactly what you were trained on, but you can't generalize to anything you haven't seen before, right? So neural networks are very prone to that because they're very powerful. They're over-parameterized, right? So you could just memorize exactly what you've been given because you have a very powerful function, right? So if you make the neural network too big, it has too many weights, too many hidden units, and the data you're trying to learn is very simple. Like if you're trying to learn a very simple linear model, you have linear data, and you give it a neural network with many weights and depth of layers, it can just memorize your function. Like it's not hard. You've got a few hundred points or a few thousand points, it'll just memorize it. So once it's memorized it, there's no guarantee that it's going to do well at a data point it's never seen before, right? Because it memorized your points exactly. So if your model's too powerful, you can actually get something that's not generalizable. That's a problem. And if your model's too small, if you keep it with too few weights, you won't be able to learn a complex function, right? So you can show examples of very small neural networks that can't learn something interesting. So all of these things come under regularization. So how do you basically alter either the data, the way you're training it, so that the model learns a generalizable, robust solution? And so you could think of, this is kind of interesting, we've talked about representation learning, like PCA and LDA and all that, right? You're trying to extract a representation from the data. Neural networks essentially do that inherently. They learn a representation internally and then use that for their task at the same time, which is why they're so powerful. And people kind of realizing that recently are using them for kind of bigger and better things. So the history of this is a little interesting, and it helps, I guess, if you're going into research to try to avoid pitfalls that other people came into, but also helps with perceptions, because if you'll say you're doing stuff with neural networks, you will get different responses. And these days, most people are fine with it because it's very powerful, but you'll get the second response is that deep learning is a fad and everyone thinks it's going to go away and it's hyped too much. So this has all happened before. Everything has happened and will happen again in artificial intelligence research. So neural networks, I guess, yeah, in the 40s, they had these ideas of doing a very simple one even earlier. Even Turing talked about simple ways of doing this. So this perceptron, which didn't really work that well at all, there was a major bug with it, which fed later to the multi-layer perceptron, was even being talked about in the 50s. And so there was this famous thing, and Marvin Minsky did a lot of AI research. He died recently, just a couple of years ago, actually. But he was very important in robotics and all kinds of other things. But back in the day, when they were first talking about what computers are and algorithms are, and they didn't even have software development languages, he basically shot down this idea of a very simple neural network, saying it doesn't even work, like it's linear, and sometimes it won't work in these particular cases, and he basically completely destroyed this idea. And everyone thought neural networks were a bad idea for a while, until people invented a way to do multiple layers and backpropagation with gradient descent, which we've talked about on the logistic part, but basically applying that idea to the network in general, which we'll talk about next if we have time. Basically applying the exact same gradient descent idea we just showed for logistic regression, but across the whole network. And so in the 80s, people, including Jeff Hinton at U of T, were working on these things, and they got them working better. And there was a new second wave of people being excited about neural networks in the 80s and 90s. So when I was a kid, neural networks were like, oh, your washing machine's got a neural network in it. It's amazing. Your toaster and this. And it's going to be everything. But they overpromised. They kind of said, because it works like the brain, it's going to learn like people, and it'll be able to do everything people can do in 10 years, and the world's going to be great. And then they thought they'd conquer things really quickly. And it turned out the brain's a little more complicated than people thought, and their neural networks were missing some parts that people didn't realize. And then actually in the 90s, there was this period of other models that worked better, right? Because the neural networks were very promising, but they didn't work robustly, and they couldn't handle nobody had really large data sets back then by today's standards. But they were very good at learning very small models exactly, but not generalizing. And so when SVMs came along and were developed, and so as we've seen, they're very powerful if you get the kernel set up properly, and they caused a lot of excitement. So people didn't do work on this and did work on SVMs. So SVMs and things like that were very popular for a long time. And anyone working on neural networks, like Jan LeCun and Jeff Hinton and Yasser Bengio and some other people, were kind of saying like, oh, you're still playing with neural networks? Like, everyone knows they're never going to work, right? But they kept trying. And so that was what was happening during this whole period. So there was stuff going on with convolution, so with images, which we'll talk about. And then there was stuff being done by Hinton. I should change this to have the names on now, since everyone knows everyone's names. This is Hinton's stuff, where he had his own models that were deep but kind of weird, like multiple layers feeding back and forth through each other for various reasons. So they have their own purposes, but they were leading to this idea of how deep learning eventually worked. We still don't have deep learning at this point. And at some point, they used RBF SVMs were kind of the most popular method, and they were doing this standard image handwriting data set, which people use a lot. And the idea for that, we'll show it when we get to images, but if you haven't seen it before, it's important for the history, and it helps with your understanding why you're is it? Oh no, your assignment 3, you don't know that yet. It helps with assignment 4, which you don't know yet, but I can still show you. So MNIST, if you haven't seen it, oops. All right, I will do this. So I'm basically going to get just stuck on the history and the high-level part here now, and we'll get into the details next time. So MNIST is a standard data set that a lot of people use. If you haven't seen it, it's really literally just people scribbling numbers, right? And they're small images, I don't know, 25 by 25 or 100 by 100, and black and white, and they're handwritten, and they have quite a variety, but everyone knows what these numbers are. So if you can classify that as these are all 5s, then you're doing pretty well, even though they're quite different. And the inputs here at the beginning were being treated as, well, people were using SVMs on this, if you can imagine, because I guess they could turn these into a high-dimensional space. So what are the features in this domain, right? You've got an image. So the features are the pixels, right? So every pixel is a 1 or a 0. It tells you whether it's white or black. And so you've got, I should know the number of pixels. So you've got 100 features for all the pixels, and they're just in the line, right? So the number of the feature, like feature 27, is some pixel here in the middle, but you don't know the feature 27 and all of its neighbors spatially are part of this hook in the 7, right? If you just treat them like a flat vector. But people were treating them as just points in this space, and then running SVM on them with RBFs and trying to do classification in that space by saying, if I find the right projection or right kernel, then all the 4s will be near each other in some weird high-dimensional, multi-hundreds of dimension space, and then I'll find a ball around those, and that's all be the 4s. So that's how people were doing it, trying to get better at like handwriting recognition, and they were doing pretty well. And so I guess around this time, the mid-aughts, Hinton and people started to be able to get neural networks to do better than that, right? And people are like, oh, what's going on? Maybe neural networks aren't a total joke anymore. And so at some point then, people started paying a little more attention during here, and at some point by 2012, they're like, it beat everyone, because this other data set called Imagenet, which I'll also show you. Imagenet is kind of the new, it's even old now, but it's the one everyone kind of used more lately. And I can't even load it because it's too big. It's a huge data set of images that people have taken from various different spaces, and it has information about what type they are. So it's great for classification because you can say, okay, show me all the cave images, and I will look at those and classify them. But it's too slow to load right now. And so there was a challenge everyone was doing at these conferences for classifying images from Imagenet. And at some point in 2012, they didn't even just beat them, they beat them by a lot, right? So they won by 10% more than, yeah, they were 10% better error rate than the next one. So all of a sudden, out of nowhere, they didn't just win, but they won by like an entire, everyone was each year at this point, by using SVMs or other things, they were making improvements of like 1% or 0.5%. And then AlexNet comes by and it's like, oh, no, we improved it by 10%. And so the next year, everyone's using neural networks. And so AlexNet's one of the first deep neural networks that uses all the tricks that people have figured out in recent years from then. It's really the start of that this deep learning revolution you hear about, that they start using it for everything. And then it continues from there. So they try to do much deeper. So even at this point, we're only talking a few hidden layers. But the inception and some of these other things we'll talk about after we get through the basics of deep learning is to make them even deeper. So 100 layers deep or 200 layers deep. And those become more and more complicated. So a fun moment that happened once around 2012, so I remember this because I'm finishing grad school. I was a postdoc. Is they Google, some of these people went to Google, so Jeff Hinton from U of T went to Google and his team were doing these other things. The YouTube one was fun because they're like using the image-based neural networks, the convolutional approaches, and trying to do unsupervised learning. They'd apply CNNs to all the images that come off of YouTube. So like the summary image from the videos on YouTube. So you got millions of images you're using, and you're doing an unsupervised point of view. So you can basically train this network, and it's got multiple layers of depth. But one thing you can do with that is to say then, like I showed you the picture at the simple level, right, when we had only one hidden network, you can imagine if you have many hidden layers, and they're actually constructed in a hierarchy, so they kind of get less and less as you go. At the top, it gives you some classification, right? So you can classify these images and figure out what they are, right? But if you do the reverse now, you can basically turn on one of these nodes at the end, say, okay, it's definitely this class, this category, and feed it backwards. You can generate a new image. You'd generate an image out of the data that you were given by feeding it backwards. And when they fed all these YouTube images back, say, find the most common thing, the most likely pattern that explains everything, and show me an image, it generated this weird ghost-like image of a cat face. And we're like, oh, YouTube's about cats. It's like, yes, correct. It figured out that YouTube was about cats, primarily. And so that was very impressive to people because it's kind of learning patterns that are there that we can interpret, even though it doesn't know what cats are. It just knows that it's a common pattern. So similar things like that happening. As I've been saying these names, these are the three people that were kind of influential in kind of pushing through that latest wave. And they recently got the Turing Award a year and a half ago, which is the best thing you can get in computer science. It's like the Nobel Prize for computer people, for software people anyways. And they each kind of were instrumental in different parts of this, right? So you've talked about WordVec. Shabenjo's group kind of was related to doing some of those things. The backpropagation gradient stuff that we'll talk about is from Hinton, and then the stuff with the images comes from LeCun. There's other people, obviously, but these are the ones that gets mentioned, so you should be familiar with their names and what they do. If you say you know deep learning, you know what they're doing, because people like referring to them that way. So that's the history part, and I guess we're at the end, so maybe that is a good place to stop, because after this I get into some other technical things about what those functions are and which different activation functions work. So yeah, I will stop there. Any comments or questions so far? This wasn't a particularly technical part. A breakthrough in GP. There could be. Yeah, there's all kinds of stuff. Like I keep adding stuff to my history. I have another slide that has even more, but I trim it for a class because we don't want to sit here talking about history forever. There were computing advances as well, for sure. I'm not as familiar about the impact of those because I focus more on the algorithms and really what happened. But at some point, GPUs became something that you can use for deep learning for neural networks. They're particularly useful for the convolutional neural nets, although now they've been tuned in to work for all of this. But yeah, I don't actually know what the particular point there was in terms of the chips. They were always available. It could have been somebody figured out that you could use them, because everybody's graphic cards that they use for video games and just for general computation, right, are very good at doing parallelized linear calculations. And so the gradient updates that you do for training, for doing backpropagation and training a network, are really just a bunch of linear operators, right? And so if you can represent the calculations you need to train a neural network in that way, then you can do a whole bunch of them in parallel. And so the distribution in the network is parallelized, so as long as for every layer at least, you can do the updates to the gradient in parallel, and it doesn't change anything as long as you combine them for the next layer. So probably maybe in 2012, what Alex is pointing out is somebody figured out how to do that directly on GPUs and then ran it, and it probably runs 100 times faster. And now, of course, NVIDIA releases cards that are specifically tuned to doing deep learning with libraries that use it fundamentally, so you don't even need to worry about it. But yeah, it's a big part of it. But I think the algorithmic part was just as important. Like, it wouldn't have been possible without the structure and the different tricks that people used to train neural networks, which is what we'll talk about next. But for today, we will end there. Thanks everyone for your questions. Yeah, you can look up the Google Cat paper. I'll try to find a paper. If someone finds it, they could share it. Because I remember it being that they used essentially the summary image from the video. It wasn't all frames, but I could be wrong about it. Okay. Yeah, so that's good. Thank you. And we'll talk online. And remember, the office hours are switched, so there'll be a TA doing office hours tomorrow. I think it's Shailja. Shailja and Benjamin are going to swap every week, take turns doing office hours, because there hasn't been that much attendance. But I will have my office hour Friday morning, and I will probably be talking about the test and give you kind of more highlights before I've released what topics are on it on Learn, but I'll release something a bit more detailed before that. And then we can talk on Friday. If you have questions about test 2, which will be a week after that, we can talk about it on Friday. And make sure you look at assignment 3 and get working on it, and check on Piazza for clarifications on some of the things that we were talking about. So until later, hope you have a good day, and go to the talk today at 1 o'clock on Zoom. Go to waterloo.ai and you can go see this talk. It should be good.